Hello, my good friends. Derek Deschamps here for Internetworking Influencers, your source for free Cisco certification training for network engineers. Welcome to day 6 of our free CCNA 100-105 ICND1 training course. The Internetworking Influencers CCNA 100-105 ICND1 training course is comprised of 13 videos, each focusing directly on a set of specific items on Cisco's official exam topic list. Today's episode will cover item 2.1, describe and verify switching concepts, including MAC learning and aging, frame switching, frame flooding, and the MAC address table. Item 2.2, interpret Ethernet frame format, and item 2.3, troubleshoot interface and cable issues, including collisions, errors, duplex, and speed. If you would like to have a look at Cisco's official exam topic list, I've included a link to it in the show notes. As a reminder, today's video has a set of free practice questions that are available on our website at internetworkinginfluencers.com that will help you brush up on the topics you learned today. The questions are a true representation of the types of questions you'll face on the actual exam, so be sure to check those out once we're done. Today we are going to start things off by looking at Ethernet frames. An Ethernet frame is used to deliver data between hosts and devices on an Ethernet LAN. IP version 4 and IP version 6 packets are encapsulated in Ethernet frames before being sent out on the physical link. An Ethernet frame is delivered based on the destination's MAC address. An 802.3 Ethernet frame consists of 7 fields. The preamble field is used for synchronization. The start of frame delimiter, or SFD field, is used to indicate that the destination address field will begin with the next bit. The destination address field contains the MAC address of the destination host. The source address field contains the MAC address of the sender. The length type field is used to indicate the type of protocol that is contained inside the data field. For example, this field could indicate that the data field contains an IP version 4 or an IP version 6 packet. The data field contains the data that the frame is carrying, such as an IP version 4 or an IP version 6 packet. The data field must be between 46 and 1500 bytes long. If there is not 46 bytes of data to be transmitted, padding will be added to the end to increase the size to 46 bytes. The frame check sequence, or FCS field, is used by the destination host to determine if the frame was damaged during transmission. A media access control address, or MAC address, is a 48-bit address that is used to deliver Ethernet frames. A MAC address can be unicast, broadcast, or multicast. A unicast MAC address is a unique 48-bit number that is assigned to each network interface card by the manufacturer. A unicast MAC address is used to send frames to a single host on an Ethernet LAN. The first 24 bits of a unicast MAC address make up the organizationally unique identifier, or OUI, which uniquely identifies the manufacturer, while the last 24 bits is a unique number assigned by the manufacturer to identify the network interface. This ensures each network interface has its own globally unique MAC address. A broadcast MAC address is the MAC address containing all Fs. A broadcast MAC address is used to send frames to every host on an Ethernet LAN. A multicast MAC address is used to send frames to a specific group of hosts on an Ethernet LAN. The first 24 bits of a multicast MAC address are represented by the hexadecimal digits 01005E. The 25th bit of a multicast MAC address is always a binary 0, while the last 23 bits of a multicast MAC address are equal to the last 23 bits of the IP version 4 multicast group address. If host A and host B were on the same subnet, and host A wanted to send an IP version 4 packet to host B, it would encapsulate the packet in an Ethernet frame, containing its own MAC address as the source and host B's MAC address as the destination. If host A and host B were on different subnets that were separated by a router, and host A wanted to send an IP version 4 packet to host B, it would encapsulate the packet in an Ethernet frame, containing its own MAC address as the source and its default router's MAC address as the destination. When the default router received the frame, it would remove the IP version 4 packet and encapsulate it in a new frame, with its outgoing interface as the source and host B's MAC address as the destination. Before sending an Ethernet frame, the sender must determine the MAC address of the destination host. For IP version 4 hosts, this is achieved by using the Address Resolution Protocol. The Address Resolution Protocol, or ARP, is used to determine the MAC address of a device from a known IP version 4 address. The MAC address is determined using ARP request and ARP reply messages. An ARP request is a broadcast message sent to all hosts on an Ethernet LAN, using the destination MAC address containing all Fs. An ARP request asks the owner of a specified IP address to reply back with its MAC address. Once a reply has been received, the result is stored in the ARP cache for future reference. An ARP request is only sent if the IP address to MAC address mapping is not already contained in the ARP cache. An ARP reply is a message sent in response to an ARP request and is sent by the owner of the IP address that was specified in the ARP request. An ARP reply contains the specified IP address along with the corresponding MAC address of the sender. For example, if host A wants to send an IP version 4 packet to host B, it would encapsulate the packet in an Ethernet frame, containing its own MAC address as the source and host B's MAC address as the destination. However, in order to do so, it would first need to determine host B's MAC address. If host A did not have host B's MAC address in its local ARP cache, it would broadcast out an ARP request by taking the destination IP address from the IP version 4 packet and requesting that the owner reply back with its MAC address. Host B would then send an ARP reply back with its MAC address. Now that host B's MAC address is known, host A would craft the frame and send it out on the physical link for delivery to host B. Now that we know how an Ethernet frame is crafted, let's take a look at how a switch forwards or switches an Ethernet frame. A MAC address table is a table containing MAC addresses and their corresponding ports. A switch uses the information in its MAC address table to determine which port to forward out a frame. When a switch receives a frame, it records the source MAC address and the port it was received on in its MAC address table. MAC address table entries can also be configured manually. These are known as static MAC addresses. Dynamically learned MAC address table entries are lost when a switch reboots. However, static MAC address table entries are retained. MAC address table entries can be deleted automatically after a period of inactivity, known as the aging time. The default aging time is 300 seconds, but can also be configured manually. When a switch receives a frame with a unicast destination MAC address that is listed in its MAC address table, it forwards the frame out the corresponding port. However, the frame will not be forwarded if the incoming port is the same as the outgoing port. When a switch receives a frame with a unicast destination MAC address that is not listed in its MAC address table, it floods the frame out all ports on the VLAN, except for the one it received it on. A switch will also flood a frame with a broadcast or multicast destination MAC address. Flooding frames can be reduced for multicast MAC addresses, however, that is beyond the scope of this exam. There are several commands for managing the MAC address table that you should be familiar with for the exam. The Show MAC address table command displays the entire contents of the MAC address table. The Show MAC address table dynamic command displays the dynamically learned MAC address table entries. The Show MAC address table dynamic address command displays the dynamically learned MAC address table entries for a specific MAC address. The Show MAC address table dynamic interface command displays the dynamically learned MAC address table entries for a specific interface. The Show MAC address table dynamic VLAN command displays the dynamically learned MAC address table entries for a specific VLAN. While the Clear MAC address table dynamic command clears the dynamically learned MAC address table entries. In this next section, we will look at some basic concepts involved when configuring switch interfaces. When two devices are connected by an Ethernet link, they can communicate in either full or half duplex. With full duplex, a device can transmit and receive frames at the same time. If two devices transmit at the same time, collisions do not occur. With half duplex, a device cannot transmit and receive frames at the same time. A device must wait for the other device to stop transmitting before sending a frame. If two devices transmit at the same time, collisions occur. A collision occurs when two half-duplex devices share an Ethernet link and both devices transmit Ethernet frames at the same time. Collisions are normal when devices are configured for half-duplex. However, collisions should not occur when devices are configured for full duplex. Carrier sense multiple access with collision detection, or CSMA CD, is a method used by half-duplex devices when accessing an Ethernet link that reduces the number of collisions. With carrier sense multiple access, or CSMA, the switch listens before transmitting. If another device is transmitting, it will wait a random amount of time before retrying. With collision detection, or CD, if the switch detects a collision, it stops transmitting and sends a jamming signal to notify other devices about the collision. The switch then waits a random amount of time before retrying. Auto-negotiation is used on switch ports that are connected to transient users or devices, and negotiates the speed and duplex settings for a link. When auto-negotiation is used, both ends of the link should be configured for auto-negotiation. When auto-negotiation succeeds, it negotiates the highest compatible speed and full duplex if supported. When auto-negotiation fails, it will attempt to detect the speed the other device is using and will match the speed. However, it cannot detect the duplex setting. If it detects the other device is using 10 megabits per second or 100 megabits per second, it will use half duplex. If it detects the other device is using 1000 megabits per second, it will use full duplex. If it is unable to detect the speed of the other device, it will use 10 megabits per second, half duplex. The shutdown command is used to disable an interface. The no shutdown command is used to enable an interface. The speed command is used to configure the speed of an interface. The speed command with the auto option is used to enable auto negotiation. The duplex command is used to configure the duplex of an interface. The duplex command with the auto option is used to enable auto negotiation. It is important to note that when two devices are connected by an Ethernet link, they must have the same speed and duplex settings. It is also important to note that if auto negotiation is configured for either speed or duplex, it will automatically be enabled for both speed and duplex. The last topic we will cover today is troubleshooting interface and cable issues. The Show Interfaces Status command can be used to display the status information for interfaces. The Show Interfaces Status command can be used to verify duplex and speed settings. A duplex or speed setting that begins with a hyphenated A indicates that the setting was obtained using auto negotiation. The Show Interfaces Status command can also be used to verify the connection status of an interface, with a status of connected, not connect, disabled, or air disabled. Connected status indicates that the physical link to the remote device is operational. Not connect status indicates that the physical link to the remote device is not operational. Not connect status can be caused by an incorrect, missing, or damaged cable, a speed mismatch, or a problem at the remote end of the link. Disabled status indicates that the interface is administratively shut down using the shutdown command. Air disabled status indicates that the switch has disabled the port due to various error conditions. Air disabled status can be caused by a duplex mismatch, a port security violation, or many other error conditions. For more detailed statistical information for interfaces, the Show Interfaces command can be used. With this command, we can see more detailed information about the status of the connection, which is separated into two parts. The interface portion refers to the physical layer status of the interface, while the line protocol portion refers to the data link layer status of the interface. For example, if both portions show up, this indicates that the interface is operational. If the interface was showing up and the line protocol was showing down, this would indicate that the physical layer is functioning. However, there is an issue at the data link layer. If the interface was showing administratively down and the line protocol was showing down disabled, this would indicate the interface was administratively shut down, using the shutdown command. If the interface was showing down and the line protocol was showing down air disabled, this would indicate the interface was in air disabled state, due to various error conditions. The Show Interfaces command also displays several counters that can be used for troubleshooting, several of which you should be familiar with for the exam. RUNTS are the number of frames received that are smaller than the minimum allowed frame size of 64 bytes. RUNTS can be caused by physical layer problems such as cabling, NIC, or port issues, or a duplex mismatch. Giants are the number of frames received that are greater than the maximum allowed frame size of 1,518 bytes. Giants are often caused by a defective network interface card, or NIC. CRC errors are the number of frames received with an incorrect checksum. CRC errors can be caused by physical layer problems, such as cabling, NIC, or port issues, a duplex mismatch, or by noise. Collisions are the number of frame collisions that occur during transmission. Collisions are normal with half duplex, but should not occur with full duplex. An excessive number of collisions can be caused by a high load or by a duplex mismatch. Late collisions are the number of frame collisions that occurred late during transmission. Late collisions can be caused by a duplex mismatch or by cabling that exceeds the maximum distance. Input errors are the number of frames received that contained errors. The input errors counter includes totals from other error counters. Output errors are the number of frames that could not be transmitted due to errors. Output errors can be caused by a small output queue. And that brings us to the end of Day 6 of Internetworking Influencers CCNA 100-105 ICND1 training course. Don't forget to complete the free practice questions for today's material, which can be found on our website at internetworkinginfluencers.com. The free questions will help highlight the key points that Cisco will expect you to know for the exam. Also, if you enjoy our free training and would like to show your support, please check out our Patreon page. We offer numerous perks to our supporters, ranging from additional practice questions and detailed study notes for each video, to direct access to our instructors to answer any questions you might have. I'll be back next time for Day 7, where I'll cover configuring VLANs, trunking, and port security. I'm Derek Deschamps for Internetworking Influencers. Thanks for watching.